As Kathy said, I'm Ben Slater with CGF Architects. My colleague Vlad Pikic was also on the invite. He's unfortunately sick today, so it's just going to be me today. So I'm very excited to present a project that's very near and dear to my heart. It's the William and Linda Frost Center for Research and Innovation. This was actually the first project I ever worked on out of school. So it's kind of grown up with me throughout my career. So very excited to be able to present it today. So quickly, just going into the learning objectives for this talk. In this presentation, you will be able to understand, hopefully at the end, how to develop a massing concept that addresses a broad range of programs that serves an increasingly diverse student body, a rigorous approach to data-informed facade design that allows for passive daylighting while optimizing for glare, and then the benefits of an active mechanical strategy that uses cascading air to create a more sustainable approach to lab mechanical design. And then finally, how natural ventilation can be used in concert with that active ventilation strategy to not only improve health outcomes, but also give users more control of the space. So first going into the massing concept, and this is kind of a general overview of the project as well, just to kind of help you understand a little bit more about it. Cal Poly, as I'm going to refer to it, is actually Cal Poly San Luis Obispo. And this university is kind of known for their Latin phrase, their motto, discere facendo, which means learn by doing. And unlike some other schools, they really do kind of live by this. It was really cool to kind of get to know some of the deans and see how they really emphasize cross-pollination between the different colleges within the campus. And that was actually the impetus for this project. Was there were 3 colleges and they all wanted, they needed new spaces, but they didn't really have money for 3 new buildings. And so they found a way to kind of come together, converge into this one building. And it really is actually quite excellent. It's more a case of something being more than the sum of its parts, we find. So just briefly, San Luis Obispo, it's kind of halfway in between Los Angeles and San Francisco, a little bit further south, but coastal California. And this is kind of a good way to understand the campus itself. It's sandwiched between the ocean and the mountains and these kind of gently rolling foothills, which are this beautiful backdrop for the whole campus. And then further zooming in, here's that site. And these are the 3 colleges which were converging on the site to build this new building. So you've got the College of Liberal Arts, the College of Agriculture, Food, and Environmental Sciences, and then the Bailey College of Science and Mathematics. And Phil Bailey, for whom that college is named, was really kind of one of the main champions in this project. He was instrumental to getting this through. And then this is a site plan of that building. You can see across the way there at the bottom of the screen, it's called the Baker Center. And this is another CGF project that we did probably 10 years before this one started. And this one was extremely successful on the campus. It also has an atrium space, and strangely, it became one of the most popular kind of hangout and collaboration spaces on the campus. We of course hope that all of our spaces do that, but this was wildly successful. And so it was a really great opportunity for us to learn from an existing building, which was right next door, and kind of take those lessons and see how we could, not mess up the stuff that was working and improve upon the stuff that maybe was less successful. And this was the final result. So it's really great to be able to show some of this finished photography, because like I said, I followed this project through kind of my career. So seeing it completed is really quite special. And I'll of course speak more about all these elements later, but this is sort of that student experience. You can see the street on the right here. This is Poly View, and this is a primarily walking street, and really the most important east-west artery on the campus. So we had a really important site that we had to treat very carefully. And you can even see in this image right here, we've sort of got this language of these volumes kind of twisting. This was something that was really important to us to create a pedestrian experience, which was not hostile, was welcoming, and felt like you were kind of integrating into the campus nicely. So the kind of key part of this learning objective is talking about how do you program a building like this, which has 3 separate kind of stakeholders within a university. Again, College of Liberal Arts, Science and Mathematics, and Agriculture and Food Sciences. Basically, this diagram was kind of a pretty good summary of that process, as I understand it. We talked with all the stakeholders, we talked with the deans, we talked with the professors, we talked with the students, and tried to distill down exactly what they needed, where those things overlapped with other college needs, how those things could then be synergized. So let's say, the College of Science and Mathematics, they need an autoclave. And also, so does the Agriculture, Food, and Environmental Sciences College. So something that maybe gets used once a day, maybe once a week, that's something that you don't need to buy two of now. So you only have the one. And it's kind of small things like this allow for 3 different colleges to come together within one building and have quite a bit more efficiency. And this extends to a bunch of these programs. Each one of these wires, which are kind of seen color-coded across the screen, those are different synergies that we're able to make between the different colleges to kind of get this to be a little bit more right-sized to fit all 3. And this was the result. So this is the graphic program. In orange, you have the true kind of laboratory spaces. That's research. The blue rectangles, those are the private offices for the professors. And then on the right side, the classrooms, that kind of larger, big one, and then the 2 smaller ones below that, those were a little bit of a late addition to the program. And those were kind of servicing this interesting change which was happening on campus. There was a push by kind of the younger guard of professors to have a different way of doing these larger format classes. The typical class is a raked floor, lecture hall, 200 plus seats. And it's quite difficult to engage with the students in the back, was what the professors were saying. In those really large lectures, it's tough to keep them engaged and really get the students to, frankly, sometimes even stay awake. And so these were thought of as a different way to kind of engage those students. So the large lecture hall, that is actually a flat floor space. And really that's with an eye on ultimate flexibility of how can you rearrange the desks? How can you allow for students to kind of look each other in the eye, but also allow for the professor to see everybody while they're speaking. And I've got some photos of that further down in the presentation. But kind of diving specifically into the labs, which are the heart and soul of this building, this idea of flexibility also extended into them. So a lab, which most people are thinking of, is a wet research lab. That's got the benches, that's got people doing titrations and so on. You can see in the middle there, that's what they call the linear equipment room. That's, I don't know if you can see my mouse here. This space right here. So this is kind of the backbone of a true wet lab. But increasingly, we're seeing that there's kind of a mixture of different types of research that are being done that maybe rely less on so much wet research. We get hybrids like the bottom left where you have wet and dry. On the bottom right, there's a project space, which is more kind of, that could even be something like a maker space where you've got 3D printers, things like that. Or teaching labs, which have minimal wet research in them, like maybe a couple of fume hoods, but not really the same intensive research. So point being, we want to be able to reconfigure these. The university wants to be able to change these things down the road. And that was really essential to how we laid out this entire building, was making sure that nothing we were doing prevented future flexibility and future renovation. So we kind of land on this neighborhood lab block. This is like the most finite unit of the building. You can see there's the lab, there's write-up spaces and collaboration, and then offices on the bottom. And we kind of, one of the main drivers of this project was that it wasn't going to just be a research intensive thing where you've got, these these like research students, which are kind of siloed away. I guess that's the word we used, but siloed away in their labs, not interacting with other students. It was really important to us that they were not doing that, that science was on display, that underclassmen could come by and see people doing, white paper research that's going to ultimately affect how things are done in the future. So the way we achieve that is by splitting the building. So you take this block, you split it open, and you make an atrium. And so this is the heart of the project here, is this science on display atrium. You can then extend it as long as you need to fit the program. And kind of the logical thing to do then would be to just lay it out orthogonally. That's what I showed in this diagram earlier. But we found that that wasn't really kind of an adequate response to the campus. We thought it made a little bit more sense to kind of fragment that form. And we came upon that conclusion when we started looking at that same campus polyview drive. So it's a relatively low slung campus. Most buildings are 2 stories or lower. So having a really large mass felt somewhat inappropriate. It also didn't respond well to the street. So we tested breaking up that block, and I think it did quite a bit to help improve that reading on the street, but also to give it a more interesting read in general of the overall massing. It also, in a later section, which I'll speak about more, gave us some opportunities to create self-shading from the building's own rotation. So kind of blocking out the sun by actually turning parts of the building. And then we took that massing and we kind of stepped it to follow a stepping site. There's actually something like 40 feet, maybe 30 feet of drop across the site. So we actually lose a floor into the ground, which is quite interesting because it allows us to kind of stack things on top of each other. And then this is an aerial rendering showing that kind of contour following the falling away site. And again, this is that lower entrance. So you enter from the lower floor, and then there's a set of stairs, which you'll see later, which take you up to the second, which is also at ground level where it meets. Okay, and then moving into the facade daylighting. This was kind of how we could evaluate how we were doing a good job on daylighting the facade. So what I mean by saying daylighting, ultimately the goal is that you wouldn't need to turn the lights on inside the building. And that's what that top metric is saying there. That's spatial daylight autonomy. And that's the percentage of the floor area, which is daylit above 300 lux for more than 55% of the year. That's 55% was something we've chosen based off many projects we've done. We found that's kind of the sweet spot. If you can get above that threshold, you're doing a pretty good job, and you're not needing to, turn the lights on inappropriately so much. Of course, that means you're letting in light, and that's great, but the issue with that then becomes glare. And so ultimately we want to let in light, but we don't want to have so much light on work surfaces that people aren't able to do the work that they're needing to do, because then they will pull the shades and then the science is no longer on display. So that was a really key directive that we got from the university, was we don't want them pulling the shades if we can avoid it. And so we kind of had to get things right and make sure that all 3 of these metrics are balanced such that people aren't pulling the shades. So the next one is annual sunlight exposure. That's basically kind of telling you how much total sunlight is getting, how much total sunlight is reaching the floor in the year. This is kind of a good proxy for just how well lit certain parts of the space are. This maybe isn't quite as important as number 1. And then number 3 is the percent of the floor area that's illuminance, percent of the floor area that is daylit during a simulation, which goes from 9 a.m. on the equinox. Again, all 3 of these are kind of approximating, is the space being well lit by the sun, and is it causing too much glare ultimately? So with those in mind, the kind of high level approach we first took was looking at how does the building shade itself and how is it shaded by adjacent things? Adjacent things being, of course, the Baker Hall across the street to the south. And you can see here, that gives us this sort of pretty heat map, which shows in blue the kind of more shaded areas, and red the areas which are receiving quite a bit of sun. And you can see on the left there, that is if there was no building across the street at all. You get a red condition basically everywhere, besides the few kind of spots where the building is shading itself. And then on the right, with Baker Hall, you get these kind of lovely gradients. And this was really interesting because this was a case of existing conditions informing the actual expression of the architecture on the facade, which was something really important to us, that the building not only perform, but it also kind of teaches how it's performing. So you can walk by and maybe a student in architecture class can have a professor come by and explain, hey, see here, like this part is quite a bit more opaque, and here's the reason why. It's from contextual shading. So we feed in these parameters. Basically, we decided that our best approach to shading the facade with a kind of dynamic response to the different shading conditions was to use a vertical fin in concert with a horizontal member. And so we had a number of parameters for each of those. The angle of the fin, how deep the overhang was, how deep the fin was. And we kind of modulated each one of those according to each face of the building in order to get the optimum performance on the inside. So again, hitting those daylight numbers, but not creating too much glare. We ran hundreds of these simulations, and one of our internal performance team members built this tool, which helped us kind of narrow down which ones of those were performing really well, getting a good balance of the different criteria that we had selected. So using the data to our advantage, basically. And then this was the result. So ultimately, we kind of got this diagram of which ways we needed the fins to be pointing in order to get that optimum lighting condition on the inside. And that was kind of a starting point for a little bit more granular discussion of how do we then fine tune each space within. So again, these were the metrics we're using. And this is a case study of a single lab on the east side of the building. But this is something we did for each and every space to make sure that we were getting that optimal daylighting condition. So this is all done as a contrast between a punch window and then our shading fin system. So punch window, this is kind of maybe what you might think of as the most prescriptive route. You just do a 40% window to wall ratio, no shading, just a punched window into a wall system. And then what we have, obviously quite a bit more glazing on the right, but our argument is that it's actually not only performing as good, but actually better than this punch window. Okay, and then this is just some drawings of the punch window. Okay, I'll go for each one and kind of the most important thing here is at the top of the screen. That's the target and then what we're actually hitting. So you can see that we've got our little happy green check mark there with no shading with a punch window. We have a target of over 55% spatial daylight autonomy. We're hitting 100% because frankly, it's getting way too much sun in the morning. And then the next metric that we have is ASE. And then this, we want it to be below 10%. It's quite a bit above at 31. So we're getting far too much kind of harsh sunlight. It's causing glare. And then lastly, illuminance. We want to be greater than 75%. So this is useful sunlight. The reason why it's red, because we actually are getting quite a bit of sunlight in here. The reason why it's red is because it's, again, quite a bit too much. So it's not helping with the, you would need to pull the shades, essentially, is what this is telling us. So we go on to our shading fins here. And again, we want to be over 55%. With this setup, we're hitting 76. So this is fantastic. We've got plenty of daylight, which is useful. And then we're also blocking out basically all of the harsh sunlight. We're below 10%, we're at 2%. You can see that one little tiny pink square there. Maybe the sun's kind of just sneaking between a couple of the fins there early in the morning, and that's creating a little bit of a bright spot. But for the most part, you could work throughout the day within this space and not have glare on your desk and could work quite comfortably without eye strain. And then lastly, we're dead on at 75% for illuminance. Again, that's because these fins are modulating the sunlight so that you're not getting very harsh glare. You're getting useful daylight out of it, basically. And then really quickly, the process of the actual articulation of the fins themselves. Early on, we had some thought that it might be kind of a heavier masonry approach with little tiny pieces of metal inserted. We got some feedback from the client that that was maybe a little too heavy, not quite in keeping with like the campus feeling that they were going for. So we revised that to be these kind of individual little fins. And initially, you can see here, we had some idea that we weren't going to use horizontals, but we found that you really kind of do need both working in concert with one another. So ultimately, this was the result. I'll kind of try to point to here. Hopefully, you can sort of see that these fins on the bottom level and on the right side here, they're a little bit smaller, they're less extreme of an angle. And that's, again, that kind of apocryphal shadow from the building behind showing up on this facade. So you kind of get, it's almost like developing a photo. You get like the negative of it. And part of that too, the actual fin material itself is an expanded metal aluminum mesh. And we chose that for a couple of reasons. One was for wind loads. But two is if you kind of zoom really close in on it, it's actually doing some light scattering itself. So it's blocking out high angle sun, it's letting in very low angle sun when you want that in the wintertime. So it's kind of the approach was holistic. It's zooming into the smallest element that should also be performing the same as the overall system. So that was really important to us, that it be working on all kind of levels. So the people next to the facade are also getting a nice experience. And this was the result from the interior. You can see here the blinds are not down. There's not a ton of harsh sunlight coming in. And it's a really nice space where you can get this beautiful floor to ceiling glass. People outside on the Polyview walk can look in and see students learning chemistry or students doing titrations. The science can be on display, basically. And then the other lovely thing about using the mesh is that at night, it kind of does a scrim effect where it becomes almost entirely translucent. And you really see this building kind of glowing out from the interior. Okay, and then getting into the mechanical ventilation side. So again, I'm going to keep talking about holistic approaches. This was really the theme of this project, was how can we make things more holistic? How can we make things do double duty? Or how can they support each other in a synergistic way? So as far as the mechanical ventilation goes, labs are pretty restrictive. You need kind of the going thinking is that you need a minimum of 6 air changes per hour. That's just to evacuate the more kind of caustic air. Also, people are performing experiments within the fume hoods that's creating like chemicals, things that you don't want. You want to move out of the space quickly. And things that you don't want, recirculating, basically. So there's kind of 2 ways you can deal with that. One of them is you can kind of take that makeup air, again, from the outside. This is kind of like the typical approach. You just do all of your intake on the roof. But we found through past projects that you can actually kind of siphon that air from the other spaces, draw it through to this negatively pressurized lab. And in that way, you're kind of getting this added benefit, this piggybacking effect of the air pulling out from the bottom of the atrium, from the offices, from the large classrooms into the labs, and it's drawing other air along with it in concert. And that's really helping to minimize the loads on the other spaces. And it also minimizes the loads in the labs itself. So it's not having additional ducting down from the roof. The fans don't have to work quite as hard. And it helps just lower any energy usage intensity in general. So that's kind of like the biggest overall move, let's say. But in concert with that, we were looking at a kind of zoned approach to how we do this. So just quickly moving through some of the plans here. And I'll go back to these in a moment. These are some of the various spaces that we go through. Here we go. So in this diagram, you can see the different mechanical zones. So on the bottom there, you have an active chilled beam in the lab. In the kind of common spaces, you have VAV systems. The offices to the north are actually fully naturally ventilated. It says with radiant heating there, and that's only turning on the wintertime. It's a pretty mild climate, so those north offices, allowing them to be naturally ventilated was really important, and that's something I'll speak more about. And then on the west side, there's natural ventilation supplemented with active chilled beams. So this again is all like we're trying to use the most efficient system for each space, but also synergistically using them together. So those active chilled beams, they pull in a pretty efficient amount of air. They're not quite as bad as a typical system, but we still have those 6 air changes we have to make. But in concert with that, we also installed an air acuity system, and that allowed us to kind of at the point of use there's basically some sensors within the lab that tell this system how much air needs to be changed. So if there's like a spill event or something, it will ramp up the air changes per hour up into the like 16, 17 numbers just to clear that air out very quickly. But if the lab isn't being used, if it's like unoccupied, it'll lower it all the way down to, I think, 2 to 4. And that's kind of represented by this little red arrow on the right side here. But that is allowing this whole system to kind of be dynamic. So it's also working with the other the other systems within the building. So it's kind of responding to itself. It's also responding to the use, all in the name of reducing energy use. So you don't want just something that's kind of dumb, just being turned on all hours of the day when no one's in there. So that was kind of the backbone of that. And a look inside the space real quick of how that cascading air works. I'll kind of try to point with my mouse here. So you've got on the right side here, those are the faculty offices. Down below, you've got the main kind of lower atrium floor with the classroom spaces. And then on the left are the labs. And we have this nice wood grill that goes across the top. And on the labs, and actually in the offices as well, it's actually got a louver behind it. So that's where that intake air is coming to perform the makeup for the 6 air changes per hour minimum in the labs. So it's kind of flowing either from the openings within the classrooms. You can see this is like a telescoping door system. So either they might leave the door open, or we've got these vents at the tops of the classes, and that's allowing for that air to escape and then make its way up with stack effect, and then out through the labs through that grill. These are just some floor plans. So this is kind of just an overview of those spaces on the interior. Again, you can see that grill at the top of the classroom brick volume in front. That's that kind of dark black metal band there. And then this is a really interesting one as well. So this is the culinary lab, like a teaching kitchen for the ag school. And so they do these classes in here, but they also have like real proper kitchen equipment, excuse me, which includes, large hoods. So again, this is another thing where we are using the makeup air from the other spaces to kind of fill that, so we're not having to provide additional ducting. And that also has a point of use system as well to make sure it's not just running at full blast all the time. Then these are the tasting labs. So these are spaces where students go into, you can see the lighting is kind of interesting back there. That's to remove some of the visual component from a dish that is being tasted, and that allows you to get a little bit more, a little bit less biased tasting of a food item. So it's a very interesting space. And then this is another example of the kind of diversity of program within the building. There's a black box theater that's on the north side of the building. And this is, again, the really interesting thing about this building was that all of these spaces are intended to be used by all 3 of the colleges. So you'll have students in here that are from the College of Liberal Arts, and they're going to be, filming something, but they will involve students from the research departments, kind of having them come in and discuss what they're doing, or maybe do a demonstration, all with eyes on, this cross-pollination concept. So nothing is really staying siloed again. Let's quickly go through. These are the zoning plans again. And lastly, here with the natural ventilation. So again, those north and west offices, these are the faculty offices. They have operable windows, which were not only important for us to put in the space because we think it's a nice thing to have, but also important because it gives these occupants an ability to control their space, the temperature, but also like if there's, let's say, a cold going around, you can open your window vent and feel a little bit safer about, having more air changes coming in. And also it was interesting on the campus. We did a tour and found that the vast majority of the offices on campus didn't have any air conditioning. That's kind of the norm there. So in terms of making things equitable, it was an interesting ask from the school that we maybe look into ways that we could avoid, having offices that do need that active air conditioning. So we did it for the most part in the north. The west was a little bit more difficult, where we needed to supplement with some active chilled beams. But the operable windows and the operable windows are working in concert. Again, the same diagram are working in concert with the other aspects of the building to allow for this kind of holistic approach to ventilation. We call this atrium kind of the lungs of the building. So you can see this arrows at the top as well. Those are pointing up through a gravity vent. And that's another passive ventilation strategy that we're using. We need those for smoke evacuation, and I'll speak a little bit about that as well, but it also allows for us to do night flush ventilation. So at night, we can open the windows, you can open up those gravity vents, and you'll get cool air from the outside coming in and flushing down through the space, pushing out the hot air. And then in the morning, you can close up all of the windows, close up the gravity vents, come in, and you've got a nice cool space that's cooled down the slabs and everything, and you don't need to turn on any of the active measures, ideally throughout most of the day. And the way we kind of achieve that integration is up at the top here on this little clear story lantern piece. We introduced a little gap at the edge. You can see this looking up. And that feeds straight up into those gravity vents on the top. And I think this is kind of an interesting view to look at of the building. The other thing that we were charged with, and we sort of charged ourselves with actually on this atrium, was to try and show as little of the services as possible. So meaning, forced air, sprinklers, lighting, power, all of the stuff we wanted to be integrated to the maximum degree possible. You can see there's some track lighting that's integrated into the bottom of the railing. We got the sprinklers, I believe, in there as well. And what we couldn't get in there is sidewall from those louvers on the top. And then air, of course, that's kind of the story here. We didn't need to have, visible supply air because our supply air is all being drawn through the laboratories. So that's pulling all of it from the other spaces for us. Again, this is talking a little bit more about that night purge ventilation. So we actually did some modeling to bear that out. At all points in this, we have a good idea, but we also want to make sure that it's actually working. So we did some modeling with our engineers to make sure that the night purge would actually work. And this is an interesting diagram. This is a wind rose. So this shows the kind of aggregate wind direction and intensity throughout the year. And you can see here, the majority of it is coming from directly northwest. And that was really important for us to know early on. We actually oriented the windows in the private offices to open towards that direction. Maybe you can't see it so well here, but all of the windows, operable windows, are pointing as much as we can towards the northwest, so that when you do open it, it's not just kind of a passive trickling in and out of the air. It's actually, you get forcible air being pushed by the wind itself. That's giving you more passive air changes per hour. So yeah, you can maybe see it in this plan here on the bottom. You've got intakes, and again, everything we're kind of trying to optimize to the site conditions there, so that northwesterly wind. The other thing we were really proud of getting naturally ventilated was our smoke evacuation. Typically, this is an active system that needs quite a bit of ducting and fans, and is energy intensive, and it's a lot of money that's ideally never used, but it is involved. It's integrated into the building. So we spoke with our engineers again. We had an ask, we wanted to do naturally ventilated smoke evac. And they were like, sure, that's possible, but we'll need to do modeling. So we did some complex fluid dynamics modeling with them, where they actually simulate a fire that starts on the ground floor. You might have remembered, like the sofa there, they basically took that sofa, estimated how much fuel was in that, and then lit a simulated fire there. And you can see on the left side, there's the time is the up and down axis. And you can see that gradient goes from a kind of blue, which is happy, that's good visibility, to black, which is very low visibility. That's that smoke kind of filling up the space. And this simulation is run out for about like an hour or so, let's say. But in concert with it, they do a study for the simulated evacuation time for each of the spaces. And you can see here, it's saying total evacuation time, I think we called out as 300 seconds. So you can see it's kind of you're getting into a situation where it's starting to fill up, but it's still navigable at that point. So again, point being, we're using data, we're using computer modeling to prove out these theories which we have and make sure that they are practicable for the space itself. Again, you can see that operable window. This is looking north, so you can see that opening is pointed towards the west, and that's that prevailing wind coming in there. And again, on a day where the wind is slow, we can supplement it with that ceiling fan, and that allows for users to control the space and allow for more kind of dialing in of that comfort. And that's essentially what this quote is speaking to. This is a study done by a number of folks, basically saying giving people the opportunity to adjust their environment builds satisfaction. So the more control you can give people, the happier they're going to be. You also need to make sure that it's working in concert with the other systems. So it can't just be something where people will open it and forget about it, and that's, you know, causing worse effects on space if it's like a smoky day outside or something. But in general, the more ways you can give people kind of control over their space, the happier they're going to be. And this is a little graph kind of speaking to that. So people tend to be more happy, more satisfied with a naturally ventilated space over a mechanically ventilated one. So where we can, we try to do that. And all of that, again, coming in concert to build a facade, which we also think looks pretty good. So all of these layers build up to not only have something that performs, but we wanted to kind of reflect the campus in a very like literal fashion. So the shading is the campus, it's the context. That's the bulk of the presentation there. I think I ended a little bit early here, so I can talk about a few other things, Kathy, if you'd like. I've got some bonus content as well.
Do we want to see if there's questions first before moving on to that? See if anybody has any questions.
Yeah,
you can say them out loud or put them in the chat and I'll read them out for you. Either way. You guys. Apparently you did it perfect.
Oh, wow. I don't know about that. I can go back. I think I sped through. Oh, sorry.
John.
What?
No, yeah, actually, I did have a question. So I see you did all your testing, and there's the theory, and then the testing of the smoke effect or the stack effect, for example. Did you end up doing any sort of commissioning after the fact to verify if it works, or is it completely based on the models at this point?
That's a very good question. I would have to speak with the rest of the team. I haven't really followed along with the commissioning side of things, but that would be something that would be good to kind of check our numbers, you know, do due diligence to make sure that it's being proven out. But I assume that's something that if we haven't done yet, we'll be looking into soon.
Cool. Yeah, I think the information gleaned from that would be really helpful for your own future designs, but also just in general for the general design industry to be able to have an example of how that works and show it in actual functioning buildings, you know.
Yeah, and I think something that maybe I briefly touched on, but I should kind of, it bears repeating. This is really one of the more ideal climates that you could build a building in. Southern California is pretty excellent. So that enabled us to do a number of these kind of naturally ventilated strategies, which otherwise might have been a hard sell or not even possible, perhaps. So I think it was a really special project in a number of ways, not least of all because of the siting. I'd like to quickly go back through just some of these earlier slides of the spaces. think these are interesting. Again, it was really important to us, like I said, this notion of integration, not only because it's a cool story, but we really think it looks nice. It creates like a really great spatial quality. I feel like as architects, a number of our favorite buildings tend to be these kind of older ones before systems became so integral to the buildings that we make. So you get very clean ceilings in a lot of these older buildings. And that was something that was really important to us, that you have, at least in the atrium, very clean ceilings. Just get to see the natural kind of raw concrete. And that also was an interesting structural challenge as well. You can see here on the right side, maybe you can kind of tell here, but the floor plates actually sort of dance in and out. They bend a little bit. And that's pushing us to a pretty extreme cantilever. So the way we dealt with that, instead of just dropping a column, was to kind of stick out these little stubby arms from the shear walls that catches the cantilever. Again, all of this to kind of maximize the cleanliness of the ceiling, but also this kind of feeling of a pure space without, interruption. I think I can maybe open up a little bit of the bonus content in the back here.
I'm actually curious about that comment that you were just talking about, making the building more simple, if you will, by integrating technologies that are utilizing passive uses, like for air, for example, not having the same sort of ductwork requirements. Did something like that also reduce the cost of the building overall, or did you find that the integration of like the louver systems and the structural system, the way you've got it, actually came out to be balanced or even more expensive?
I think I would need to go back and double check. I'm kind of speaking a little bit out of turn here, but I do actually think it was cheaper on the mechanical side. Now, granted, I say that this kind of cascading air approach is something at ZGF we do on all of our labs. We think it's a really kind of clean solution, but in concert with the atrium, with those naturally ventilated strategies, it did save us ductwork. It saved us additional units, fans, all of these things which you don't need. I have to believe that it saved some money, which again, all of this was in service of trying to create more amenities for the students. So every dollar we could save on the mechanical system is a dollar we can put into making the classrooms all that much better. I think speaking of the classrooms, these were some diagrams that I should have pulled up earlier, but this is kind of that typical lecture hall layout that I was speaking about. And this was the layout that we landed on ultimately. Granted, it's flexible, so they can change it however they want, but this is the primary configuration that they use. And what's interesting about this is it's a great idea, like put the professor in the center. It's the shortest distance possible to all the students. But then how do they see the screen? Because typically you only have one screen. And the answer to that was you put 4 screens, a screen on each wall. And it did take some convincing, ultimately, of the professors. The younger ones, the kind of newer professors, were a bit more welcoming of this kind of new approach. They were on board. They were like, great, I get to look my students in the face. I'm never more than 4 rows away from a student. Some of the professors that had been doing it for a little bit longer, it was definitely an adjustment, placing them in the middle of the room. You're kind of beset on all sides. You have to, turn and point. You have to orient yourself in the space to kind of what's going on the different screens. I think I have some actual built photos in here as well. Those were renderings. But it bears out, the students really love it. They, anecdotally, the professors say that they have quite a bit more focus. It's a little bit harder to quantify something like that, but just better engagement in general in the classes from what they're saying. And this is that central configuration again. So it's, this kind of Socratic ideal of everybody sitting in around. You can ask questions of one another, learn from each other, learn by doing. All of these really noble ideas, but we found a way through a lot of stakeholder meetings, a lot of research of other universities, what's working, what's not working. How can you make that happen in a space, and how can you make it better for students? And actually the furniture, furniture was another key component in that as well, to making the experience better. One of the interesting quotes was from a left-handed student saying he just hated the typical wooden desk with that kind of L-shaped thing that's all attached to the seat. And that struck a chord in me. I'm left-handed as well, so that was a persistent experience throughout college of this desk, which is really designed for most of the population, but not really serving everybody perfectly. And so a great solution to that is movable furniture. You've got a separate chair, you've got a separate table. If you want to do a breakout thing, you can rearrange the desk very quickly into smaller 4-person groups. It just gives a lot of flexibility. Actually, on opening day, I wish I had the photo of this, but opening day, they cleared out all of the tables and they had a huge banquet in here. So it just gives the university not only a really great teaching space, but a great flexible multi-use space that they can come do all kinds of different things. And we kind of just provide that power infrastructure and the IT infrastructure for them to kind of do with it as they need.
So what is the seating capacity inside of those spaces then? Because like you said, a lot of lecture halls might have like 200 plus. Can you get that many people inside one of those?
That's a good question. Let me pull up my diagram here. So yes, initially what they asked us for was a 250 seat raked floor lecture hall. In our current configuration, it seats only about 200, but we can seat that more typical kind of configuration, which is the first one I showed here. We can seat that 250 in a more typical lecture format. Granted, they don't do that very often. I don't think they've actually done it yet since moving in, but the option is there if they need to do a larger lecture course. They can reconfigure that pretty quickly. And then this configuration is that one that I was talking about. You can do smaller breakout, group collaboration for people things. So it's a very, very interesting space. A lot of research went into this to make this one happen. And it was not without its detractors initially, but now everybody seems to really love it. So we feel like we've done something good, something successful.
Ben, I have a couple questions if you're at a time to answer those.
Absolutely.
I really like this project. I think the building's beautiful. I have a programming question. This reminds me of having these 3 disciplines in the same building of the MIT Stata building that Frank Gehry designed back in 2004. And the programming that was given to him was the idea that MIT had lost some of its sort of significance in terms of its major buildings and their academic aspects. And so they decided to put 3 or 4 or 5 very different academic units into the same building. And I think they had artificial intelligence, linguistics, philosophy. And the idea would be that they would try to put them in a position where they would interact with each other so they would learn something beyond their own disciplines. Was there any discussion about that, of having these disciplines that are very different in the same building?
Yeah, that was actually front and central. So we had a really progressive leadership group from the different colleges, and this was their #1 goal, was to have that cross-pollination. Not only to get a really nice space, but I think ultimately their hope was that more students would interact that otherwise never would have. And a really interesting
post-evaluation idea about how's it working?
So supposedly quite well. So an interesting kind of anecdote they told me was they had a group of students working on a project. Otherwise, this would have been really difficult because they were all siloed away in separate buildings.
Right.
This particular project was for a solar-powered cooler, and this was to be implemented on indigenous reservations where access to refrigerators is pretty limited. Our infrastructure was limited, so you had like the architect designing the container, you had the engineer doing the refrigerant loop and the solar power. You've got the liberal arts anthropology students kind of working with population, helping understand like what are the cultural implications of this thing. And they're all working in concert. And then you've got the business students, you know, trying to see how you could implement this and upscale it to market, to get it to, you know, several reservations. So at least from what they're telling us, it sounds like it's quite successful. You get these students that otherwise wouldn't really be talking to each other, or it would be quite difficult for them to, you know, find time to go do that.
Right.
And I think that's maybe our best marker of success on this project. Let me see if I can find this photo. Yeah. These spaces outside of the faculty offices. So on this side, this is the kind of public, open to really anybody who comes in, all the undergrads, everybody. And then you can maybe see right here, there's a glass security barrier. That's to kind of protect, you know, the research students leave their laptops and stuff out in the writing space over here. So you can't just have anybody wandering in. That being said, it's open on levels 2 through 3, so people can kind of, you know, yell across at each other.
Right.
But what we've seen happen is you see students from different colleges sitting at these collaboration areas together and just chatting, having moments, maybe not even stuff that has to do with school, what they're talking about, but just life moments, you know, meeting other people.
Sure.
I think, you know, something that came out from the pandemic is people got quite a bit more, you know, siloed away in their own lives. And it's really heartwarming to come to university, see all these kind of younger folks all just chatting with each other,
Right.
and maybe hope on some level that our space is facilitating that.
Great, thank you. I was especially interested in viewing this presentation. I spent my first 2 years at Cal Poly, and so it was a special interest. And I was hoping that Katie Hall, Eugene architect, might be on here because she graduated from Cal Poly also.
Yeah, we really had to get this one right because our managing partner at the time it's his alma mater. So he made it clear we had to really hit a home run here.
Exactly. Thank you.
Yeah.
Do we have
All right,
any other
Ben.
questions?
Yeah, Ben, I had one other question, and this is a kind of a tricky one too. You've got chemistry and food production and classrooms and offices and everything like that put together, and you're mainly using a passive air circulation system. How do you deal with cross-contamination of odors throughout the building? I'm
Yeah,
just wondering
so
how like a chemical, you know, or the chemistry might produce something that might damage the food production or vice versa.
that is a great question. So that's kind of where this diagram comes into play. So as much as possible, everything was passively ventilated, but in the lab spaces and in the culinary lab spaces, they are actively ventilated. So the exhaust, that's that 6 air changes per hour high exhaust rate that's going through there. So, you know, you've been in spaces where you kind of open the door and it's sucked open, you kind of get that air rushing in. That's a negative pressurization. And that's true for all labs that we do. They're all negatively pressurized so that, you know, if there is a spill, if there is a contaminant that's released, it's always going up and out through the exhaust. It's never coming back into the main space. So that that's also where we have that cool air acuity system that's constantly monitoring for contaminants that are in places where they shouldn't be. So ideally, you're working in a fume hood, and if you spill a chemical, it's just going straight up through the fume hood. But if somebody like spills a bunch of acetone on the floor, that's obviously going to reek up the space. But you've got the system that's going to detect that, and then it's going to just start cramming air through the space as quickly as possible to get that out. And none of that is coming back in through into the space in the atrium. And likewise for the culinary space, we also have a kind of dynamic system on those hoods as well. So they can tell when people are cooking, when there's a lot of particulate matter, it'll ramp up the exhaust. And we also were sure to locate our exhaust stacks far away from intakes. So with all the wind modeling that we did, not only for the passive ventilation, we're also making sure we're not, you know, recycling any bad air, basically.
Nice. That's great. Thanks.
Mm-hmm.
well, we are coming up on time. So if there's any last questions, let's get to those. Otherwise, I think we can safely conclude. Thank you so much, Ben. This was great. We really appreciate your time.
Yeah, thanks so much. That was an awesome presentation. Really cool building.
Thank you. Yeah, and thank you all for really great questions. It was a kind of fun learning process doing this, because like I said, I was pretty junior when I started on this project. So it was fun for me to kind of go back and do some research about my own project. It's a really good opportunity.
All right. Well, thank you, everyone, and we'll see you at the next one.
Thank you. Thank you, Ben.
Thank you.
Bye, everyone.